Welcome and thank you everybody for joining us in person and online for today's C2 Smarter seminar and the next installment of the Structural Health Monitoring series, which is co-hosted by Rutgers and their Rhine Bridge Resource Program. Today's seminar is titled The Intersection of Cloud Computing and Civil Infrastructure. And before we get into the seminar, just a reminder that we will be recording the presentation and then uploading it to our YouTube channel. And today we are joined by Eric Zucker and Rob Wildish, both of HNTB. And Eric is a structural engineer in their New York Bridge Group and has more than 14 years of experience in the bridge industry. And Rob is a structural engineer in HNTB's New York Bridge Group and started there full-time last year after interning part-time while pursuing his master's degree. And we encourage everybody to ask questions. If you're in person, you can do it as the presentation rolls along. And if you're joining online, you can press the Q&A button, which is at the bottom of the Zoom window. And then we can read out your questions at the end of the presentation. And with that, I will hand things over to Eric and Rob to get us started.
All right, thank you so much. So today we're going to talk about cloud computing and civil infrastructure. And I would say the C2 Smarter Center is probably the exception to the rule, but for most places in our industry, these two things are not often discussed in the same breath. There's much that we do in the civil infrastructure space that does not rely on and does not utilize the best that cloud computing has to offer, especially looking at massive data sets. So what we'll talk about today is sort of the basic entry points into cloud computing and the ways we found them to be valuable in the area of civil infrastructure. So over the past 2 years, myself and Rob, since he joined the company, have been involved in this space. And we really find it very approachable in general, once you know the basics. If that's really the goal today, is to convey to people what is going on with cloud computing, how can it be utilized by everyday engineers to better their current practice. And so just to talk about infrastructure in general, I spared you all the slide about how infrastructure is so deteriorated, but we know that that is happening. We know there's the ASCE report card that talks about the various needs that we have in our nation's infrastructure. We know that much of our infrastructure built in the 50s and 60s is nearing the end of its useful life. And we also know at the same time that freight trends have changed no time more than the past 3 or 4 years since the pandemic. And so with those changing trends in freight, we really have to experience and explore what that means for our civil infrastructure. And finally, so many changes are happening with extreme weather, where we're getting various things occurring now that have never occurred before. And so with those as the current challenges facing us, the good news is we have all these tools at our disposal. Not only massive data sets that many have only come online a few years ago, but also these tools in the sort of technology suite that have become, for the most part, cheap or open source and available to anyone willing to learn. And so the 4 key places technology we'll talk about today are shown on the right. One is programming. We'll focus on the Python language. One is machine learning. We'll give an example or two from the scikit-learn package in Python. We'll look at AWS and the cloud resources they provide, many of them similar to in Azure provided as another cloud resource. And then Power BI as one example of a data visualization dashboard that we have. And so I think because the challenges we mentioned, and because of technology we now have to understand it better, the 20 years will look nothing like the last 100, and it's up to today's engineering generations, and those who are interested to really figure out these problems. And so like I said, our goal is to lower the barrier to entry for all of you to understand the cloud computing more than you hopefully already do. And so when I try to explain this to people this entire hour long into a single sentence, I usually say, the engineers who know our infrastructure problems inside and out deserve to have the data tools to know the data inside and out. And so now with that one summary sentence, you can all go on your way, maybe knowing exactly what you're going to learn, but hopefully there'll be a few more good examples. And so our agenda today, we're going to touch on just the aspect of bridge capacity and demand and looking at that. As you heard in our bios, Rob and I are both bridge engineers and structural engineers, so that is the perspective we're approaching this with. But I think the lessons learned really would apply to many other disciplines of engineering within civil infrastructure. We'll touch on those 4 technologies: programming, machine learning, cloud computing, and visualization, and the way that all of these tie together in a cohesive way. And the 2 examples we're going to use, not so much on specific case studies, but instead on 2 meta topics that we think are really primed to experience all of these various data technologies and the advances we can make. one of which is freight, specifically looking at weight and motion data, and the other is looking at extreme precipitation and the way that affects our civil infrastructure. And so this is our bio page, just to give you a little bit more about us and kind of give you the background of where we're coming from. We tried to look for some photos of Rob on the bridge and we couldn't find any, so both these photos are me. We'll have to get some better shots of Rob in the future. And so, like they said, I've been at HNTB 14 years. I serve as our company's bridge technology lead alongside one other engineer. And so really firm-wide, any bridge technology aspect lands in my desk one way or another. I've been fortunate enough to serve as not only an inspector and designer, but also help out with the construction phase as well and really run the whole gambit of bridge engineering in general. And then Rob, I have nothing but good things to say about him. He's only been HNTB full-time for less than a year. He had an internship with us while he finished his master's at Columbia and has been able to really take on a lot of additional responsibilities because he has the skill sets that we're going to talk about today. And not only him, but also two other interns we had over the past summer had Python experience and were willing to teach themselves things like ArcGIS and Power BI, these softwares and programs. We were able to utilize them and really make a lot more of their internship and their skill sets than we would have otherwise. So I really see this area as a way to expand skill sets for young engineers. And so this for me is the why are we here slide. You know, we probably all, at least some of us, recognize the LRFD methodology shown really with the probability and the curves here. We have a certain amount of load that we expect, and we know there's a bell curve of statistics of where those extremes may be, and our structures based on different variabilities have a certain amount of resistance. Our goal as engineers is to minimize, or if we can, eliminate the overlap between those two curves. Now the problem we're having is that the loads that we're seeing from both weather and from freight are shifting that yellow curve and that oranges curve to the right. These loads are increasing. At the same time, because our civil infrastructure is nearing the end of its useful life in some cases and deteriorating, the blue curve is moving to the left. So we're increasing the amount of area and overlap we have between these spaces. And so with those shifting curves, we think it's even more important today than ever before to truly understand what are the demands and capacities of our structures. And by using data tools we'll talk about today, we think we can do that more effectively. Every time we try to sharpen our pencils on what these loads or capacities would be, we find ourselves surprised, where in some cases, the code is unconservative, in many cases, it's overly conservative, but in any case, we want to have that information at the hands of engineers who are making those most complex decisions. And so the circle we see there, the design, inspection, analysis, and retrofit, is really the virtuous cycle we see. Data and technology should be integrated into all of these pieces, and that allows us to continue to look more and more at how these fit together. And so usually when you have a cloud computing or a big data presentation, you start off with one of these three graphics, either lots of floating ones and zeros or cool 3D graphics, or maybe some plot about how data is doubling every so many years. But for me, I don't want to talk about big data in that sense. What I want to talk about is how data, I see it and I explain it to others as like a flashlight. Having data, having technology, having an awareness of the world around us does not change the physical world, just like a flashlight would not, but it allows you to navigate a better path forward and to avoid any pitfalls because you can actually see more clearly what's going on. As an engineer, I don't want to have data sets sitting on my servers that I'm not able to post-process effectively or to analyze effectively, but for the tools that I could have had otherwise. And so I feel like it's our imperative to understand these sometimes very arduous and large data sets and the implication for the structures that we design and we're rehabilitating. So I brainstormed with a few colleagues a little while ago on what are the types of data we deal with on an everyday basis. There's this sense among many engineers who don't see this as kind of their forte, as I'm not a data scientist, I'm not a technology person, I'm just an engineer, I just do bridges, I just do structures. And if you look here in this list, many of these things would seem commonplace to those people and those staff members of our team. And so my argument here is that really all of us are working in the data space, whether we know it or not. And ultimately, if we can find better ways to more effectively process these, as well as have repeated lessons learned carry forward, we will all be better off, and our industry as a whole will be better off. And so the sort of paradigm that I've tried to push among other HNTB engineers is this idea of medium data. It feels like there's this sort of false dichotomy between either you work with Excel, and once Excel's maxed out, that's all there is to it. or you hire a team of 10 software engineers and you shoot for the moon, you do this amazing thing, and you get to write lots of great articles about it. The piece that I'm seeing is that with tools like Python and data visualization and even some cloud resources, there's this whole middle piece, this medium data. That's not big data. It doesn't take 10 software engineers. It takes a bridge engineer or some other type of engineer who understands the middle piece and can use data sets well beyond what Excel and the 1.4 million rows to do more. I think this is a key aspect of risk mitigation, again, for us to understand the data sets that sit on our servers and sit publicly available that we have access to. And I think this will be a key advantage for structural engineers in facing tomorrow's challenges. Let's see. And so I crossed out emerging here. I feel like, this is, when we talk about this typically among engineers, we say this is emerging technology. Amazon Web Service has been around for 18 years. Python has been around for nearly double that. And so these technologies that are nearly as old as I am, it's hard to call them emerging technologies. They're just simply new to the space of engineering. And so again, there's the 4 technologies we're going to talk about today. I want to do a quick show of hands, at least those in the room. Who has worked on using programming languages before, Python, MATLAB, or something else? Okay, good number of people. Who's done machine learning as part of a lab or an assignment? Some of you, yep. Data visualization, I'm sure, goes along with all those things. But this is the tough one. Who's actually used cloud resources, gone into AWS or gone into Azure, and apportioned those things to help you solve a problem? Okay, no hands go up that I'm saying. So I think that's really the key, is that those 3 other tools can be supercharged by what you can do in the cloud, and it's really very approachable, and that's what I want to try to convey today. And I'll actually give some prices of what we've had to use, most of them measured in pennies, just to show you how cheap these things have been that we've been able to utilize, and how it really makes sense to leverage and lean into this space. So just to start at the beginning, I have one slide on Python. Doesn't really do the language Python justice to do it in one slide, but I think most of you are hopefully familiar. It's very similar to MATLAB, and it's free and open source. In my opinion, it really has become the universal language of data that allows us to do this. I've heard it said that Python is not the best language for anything, but it's the second best language for everything, because there's always a package that goes along with this. And so for all these pursuits, really the backbone, the glue that holds these together is the Python language, because it has connectivity to everything else. One simple way to do this, if you're at home and don't have access that you know of, you can go to Google Colab. That's shown in the middle right there. And basically anybody can go to colab.com with your Google account that just about everybody in the world has, and you can start typing in scripting. I've also found, and this discovery predates the slide, or is after the slide was created, but ChatGPT is really very handy in being able to ask it certain questions and say, explain, I want to do these things, and it will give you at least sample code. Obviously, you're still responsible for what that code does or doesn't do, but it's a great way for those who are beginning to understand the types of packages and initial commands you can use. So I'm not going to go in depth on all these things, but just there's a lot you can do with this, and this really is the glue. If everything you hear today is interesting, this would be the first and best place to start. And we use Python for any number of things. Structural monitoring is something that both Rob and I specialize in and do quite a bit. We've been able to use, in some cases, millions of rows worth of data and use Python to very effectively and very quickly post-process that down into a visualization or an analysis or post-process that we can never glean the findings from that data and ask it specific questions to understand what's going on. And so machine learning is, arguably the hottest topic today in technology, and really even it's breaking so much into the civil infrastructure space. So I'm not going to go over the latest and greatest of machine learning, because I think we hear that in just about every BuzzFeed article or Medium article that's out there, and we're getting bombarded constantly with things like ChatGPT. What I want to do is go back to the basics of machine learning, and especially talk about some of the pitfalls that we have. Just one more show of hands, because I forgot what the answer was. How many in the room have used machine learning to some degree? Yeah, so a handful, maybe about half or a third. And so, ultimately machine learning is simply looking at data, rendering a prediction based on that data, and then giving us a decision. It is up to us as the engineers, as the people, the professionals who are looking at this, to understand what that decision means and whether or not we trust it. And so, like I said, Python and scikit-learn specifically is a good entry point for machine learning, are sort of the lower end of the complexity spectrum, and they're free. TensorFlow, which has a Keras front end, is probably the upper bound, at least, of the neural network space. There's now various generative AI environments you can also leverage. And so the challenges I see as a structural engineer are, number one, getting enough quality data to train it on. If I want to do something simple like look at bridge behavior, I may have thousands of entry points, years worth of data for those structural parameters. If I want to look at, let's say, connection design and have a steel bolted connection and try to do machine learning on that, I've got to somehow synthesize and gather examples from all over the industry into one cohesive database. A much greater challenge, although potentially very valuable for us to do. We also have to think about what is the implication of the error rate. If I'm simply using computer vision and I'm trying to track something across the screen and that tracker doesn't go very well, nobody really gets hurt. If I'm using this on machine learning data to try to predict when there's a structural issue, that could be a significant problem if I'm relying too heavily on that machine learning algorithm. And so we do find it challenging as well. We can have data, we can have it render predictions, but making those actionable truly is a challenge. And often, just like some of the structural monitoring software used, the finite element software, it can be like a black box with unclear inner mechanisms that we have. And so I think this is, most of you will understand this, but that we have sort of two types of data: structured data in the columns you'd expect, and unstructured things like photos and LiDAR and sound waves, which really don't fall into that clean column example that's typically out there. These are just a handful of machine learning algorithms. I'm not going to go in depth on any of these, but just to talk about, there are multiple ways, and often we find that certain algorithms work much better than others on different types of problems. And I do have an example in a minute to show how we're able to iterate through those very quickly. Typically in machine learning, you have a training set and a test set. Sometimes if you're doing more complex evaluations, you can have a validation set so you can constantly iterate through, hone your parameters, and then test the data eventually. I think this idea of under or overfitting is best shown by these three plots on the bottom. Obviously, our goal is to have that middle plot where we're easily tracking the data, as opposed to trying to be too precise or not precise enough. Now, this is very simple to visualize. You could probably draw that line yourself in Microsoft Paint. The challenge is when we have not only two dimensions like we're showing here, but in some cases dozens and dozens of dimensional space, we have to still try to meet all of these factors without overfitting. And so this is just one very simple example that we ran through in the beginning of our machine learning exercises. This is not, I would say, an active HNTB initiative to predict concrete strength. This is more proof of concept, just to give that caveat. But what we found was about 1,000 or so concrete breaks. We had all the parameters: slag, fly ash, coarse, and fine aggregates. And we tried to use those inputs and those materials to predict what the strength of concrete would be based on the known values in this set. The nice thing about scikit-learn, which is what that screenshot is shown there, that black box is a screenshot of Excel or of Python, is that you can import all these different types of machine learning engines, and the format between all of them is very similar. And so you can actually just go through each one individually, all with the same post-processing and pre-processing at the front and back end. You can then try multiple types of machine learning algorithms and even hone their various parameters very quickly to iterate through. The best we're able to do is that plot on the top right, where we have, I forgot to label the axis, but that's I believe it's the actual strength on the bottom in PSI or KSI. Yeah, this would be actually pascals, but so on strength on the bottom, actual, and predicted on the y-axis. And you can see that in general, they follow that blue line, but however, we're really not able to get any more accurate than what we're shown here. And I think that points out something that really applies deeply to the machine learning space, which is there is inherent vulnerability or inherent variability in much of our work. And so no matter how closely we were honed in this, even some concrete samples from the same batch of concrete still had a multiple variation of up to 20%. And so when we approach machine learning, really the ideal place for that to be, the ideal problems to solve, are when things are both complex and narrow, valuable and low stakes, which sounds like four complex parameters. But the example I give is the headlights. For those of you who drive and you have one of the newer cars, there's automatic brights that go on when there's no car in front of you. When a car starts coming at you, it will put the lights back from high beam down to low beam. And that's being solved by a machine learning chip in your car and a very basic computer vision algorithm. This is a complex task. It's not something that you can simply say, if 5, then lower or something else. There's no if-then statement. It is complex. But it's also a very narrow thing you're asking that machine learning algorithm to do. It's valuable because it takes one thing away from drivers who might be distracted otherwise. And it's also low stakes. If we end up shining the brights when we shouldn't be, we just turn them off and the driver is able to go on. And so this slide is from, I believe, 2.5 years ago when I first presented to the C2 Smart Center. And I left in there almost for posterity. 2.5 years ago, I had to explain what the applications of machine learning would be in our field. Today, I feel like it's almost commonplace and everyone has an understanding of this. So just to say, in 2.5 years, I feel like the industry has progressed so significantly on the way this really has implications for our various fields. Okay, so now I'm going to go through cloud computing and then we'll go into some of these case studies. As I said, at least my perspective is out in the real world away from academia, this overlap between civil engineers and data scientists or the tech and data sector is lacking, or at least there's a big opportunity space for us to gain more from these. Cloud computing is the basis of just about everything we do. Every app, every social media, every various streaming software, just about everything relies to some degree on cloud computing. And so while there is minimal crossover, it's going to be essential in the future to have these dual skill sets and to utilize these things. And so at its core, cloud computing is simply a bunch of data centers where you can rent or apportion certain amounts of cloud storage or software very efficiently and with a high resolution network connection. It's what allows us to have shared documents like Google Docs and have people from multiple places all going into the same exact place and server. It allows for real-time visualization wherever we use a dashboard. And it also is able to allow us to automate things more readily. Just a few more things. You can connect from anywhere, collaboration I mentioned, and there's also a lot of third-party software that's available to those who are getting into the weeds on cloud computing to make it more efficient for you. Just to touch on one thing, the nominal price. So we had one algorithm in the cloud that's running every 30 minutes around the clock. It is gathering data from a database and putting it into our own database in a post-process manner. And so when we ran that algorithm every 30 minutes, 24/7 for an entire month, the cost that it cost us was only 2 cents. And so, I was supposed to go fill out my expense report. My boss would have laughed me out of the room if I handed in a 2-cent expense report. But that just speaks to these values that we have and how we can use them. Yeah.
What was the algorithm doing that needed it to run every 30 minutes for a month?
Yep, that's a good question. So the question is, what was the algorithm doing that we needed to run nonstop? And so this was looking at live traffic data. If you go to Google Traffic, instead of the red, green, and yellow on your phone, it's actually backed up by numbers in a database. You can access those via API. So for specific key routes along different roads, our client wanted to understand can we quantify the traffic congestion along those routes around the clock? And so every 30 minutes we were saying from point A to point B that we specified, what is the travel time? We were building a database and then visualizing that data on its own so they could say, well, on Friday we had 2 extra lane closures because of construction. How did that affect our congestion and the average speed at different times? Yeah, good question though. So just to break down Amazon Web Service, I think this is a little bit old data, but I mean $62 billion. This is a massive industry. And really the 2 key players are AWS, which is Amazon Web Services, and Azure. Everyone else is really kind of the also-rans. There's IBM, Alibaba, Google, but altogether they make up a smaller portion typically than these other 2 together. And so AWS offers about 200 different services. I'm going to quickly go through 16 of them today. I'll do it very efficiently so as not to bore anyone. But just to show you when I talk about cloud resources, what am I talking about? The entire top row here are various ways to store data in the cloud. S3 is typically just a simple folder structure like you'd have on your Microsoft computer. SQL and relational databases, some of you would be familiar with, is just a way to hold structured data in the cloud. There's also various databases we have with Redshift and DynamoDB are more the enterprise level data storage systems. On the computation side, an EC2, an Elastic Compute Cloud, is basically a desktop you're renting in the cloud. When we think about remote desktoping into one of the computers somewhere else, it's like having one of those in the cloud, and those can be as cheap as 5 cents per hour. Same thing with SageMaker, which is just a Jupyter notebook hosted in the cloud. Google or AWS owns the computation power for that. Again, 5 cents per hour. There's also software development and these serverless compute functions, which is the one I talked about running every 30 minutes on its own. Those are called Lambdas. Just a few more services. That whole top row is all ways to configure your other services in a more security sensitive way. So there's a whole security suite built out around this. And the bottom are all sort of various types of aspects you can keep track of your cost. If you're a streaming service, you can use delivery networks with content delivery all over the world. My favorite one is a snowmobile, where they actually, AWS has their own big rigs. They'll pull up to your facility and they'll download terabytes worth of data onto their hard drive and then go plug it into the cloud for you, so you're not taking up your large connection. And then visualization dashboards like QuickSight. And so we're used to this term now as a service, but really there's sort of four aspects of this. There's probably more if you really got into the weeds on it. Infrastructure is simply apportioning physical things in the cloud and saying, well, I'm going to rent this server for a certain time. Platform would be when you're actually designing software. Software as a service is any app on your phone. And then desktop as a service, obviously, is when you rent a physical desktop in the cloud. And just to touch briefly on visualization, really all the things we've talked about can feed into helping us better post-process and visualize this data. So this that's shown on the top right is a good way to show we can do both GIS data to show in a map where these things are, a really great way to look for trends. And Power BI is our go-to. I don't know about different organizations, but at least with H&TB's Microsoft deal, every single employee of ours has access to Power BI for free. Many of the Office 365 suites do have access. This allows us to look at data and zoom in where we want to. It's really accessible. You're putting this in the hands of those who don't have a data background to be able to ask questions of the data by doing filters and toggles and triggers and different parameters, so they can look into the data and ask those types of questions without ever having to touch Python. It allows us to identify trends over time. And I think broadly, since the 60s when computers first came into the mainstream, the paradigm has always been that the best interactions we have are when humans and computers work together. I think that's just as true today as it was back in the 60s. What dashboarding and visualization can do for us is allow us to look at broad swaths of data, filter down to the pieces we care about or are called to those. If I see a spike, I might zoom in on that spike and see why an anomaly is happening, and allows me to use my human analysis abilities to the best degree without being overwhelmed by millions and millions of records. So just a few more things. These are sort of the four big ones, at least for me. Amazon has QuickSight. Tableau is its own just visualization dashboard. Power BI I mentioned. And Grafana, I believe, is still a free dashboard or has a free version of it. Any Excel file, even just a CSV or Excel file, can be fed into these and initially start to be visualized. With that, I'm going to hand it over to Rob.
Thank you, Eric.
On the ground.
Hello, everybody. I'm going to be talking a bit to you guys about Way in Motion, referred to as WIM often, what it is, why it's important, how it connects to cloud computing, and some examples of how we use this in our work. So what is Way in Motion? Way in Motion is collecting vehicle data as it passes through a certain location. So that is recording vehicle speed, axle weights, axle spacings, direction, which lane they're traveling in, and even more. It can be integrated with tolling and other transportation systems, but it can be anywhere on the road, really. And it often comes as in larger data sets. We're recording all this information for every vehicle passing a certain point. So it's kind of like that medium data area Eric was talking about, where these files are often too large to open and manipulate in Excel. And that's why we often turn to programming languages like Python to work with them. So why is WIM important? WIM is very useful for understanding the actual vehicle live loads that our bridges are undergoing versus what we assumed when we designed the bridge. For example, the design vehicle currently in AASHTO, the Bridge Design Code, was based off data from Kitchener, Ontario, a more rural area in Canada from 1975. So understanding how the vehicles and trucks coming into and out of New York City 50 years later and how they may differ from that is critical to making sure we're designing our bridges to adequately high live loads. not only for strength design, but also for fatigue design, where the volume of cars, how many cycles we're seeing across our bridges is useful for fatigue assumptions, but also other assumptions that rely on volume, such as multiple present factors, which relate to how many vehicles are crossing a bridge at the same time, where, and other things such as freight network, tolling and the effects it has, permitting and its enforcement. So how do we process this data as it comes in? We often receive raw data from clients, whether that be for a specific location, a bridge, or for a network of stations that could be nationwide, statewide. And when we receive that data as raw data, it's not really readable. You can't get anything from it, so we have to run it through a program that interprets the data, categorizes it before we put it into a cloud storage bucket where it's uploaded to the cloud. Sorry, I should have said that first, but it's in the cloud now. And from there, we have two options. If we want just more summary level data, want to understand basic trends about what we're seeing at that station, we can transform it into curated tables and then turn it into data visualizations, Power BI dashboards that show our clients or for use internally what we want to see from that location. But if we want something more in depth from that station, such as a more specific trend that needs more filters, or we want to compare it to non-WIM information, we will often run it through other customized data protocols, another program, before putting in those tables and dashboards. An example of this is from some nationwide WIM data we received from a client. We were able to turn that into a nationwide weigh in motion dashboard that showed vehicle trends, it helped us understand real truck behavior and how it varied with two external factors. For example, top right, an example of what this dashboard showed was how the amount of trucks we were seeing over 80,000 pounds, the legal limit, compared to gas prices. So from that plot, we were able to see that as gas prices increase, there is a positive correlation with the increase in a positive linear correlation with the amount of trucks we're seeing over 80,000 pounds, suggesting carriers were risking overloading their trucks to decrease the amount of trips they would have to make. The bottom right was a screenshot from a graphic that showed the concentration of overweight trucks at different locations. The bigger the circle, the more overweight trucks there is. And as you zoomed in on that graph, or that map, what made it interesting is it became more granular. So those circles would split into smaller circles along major freight routes, and you could track the amount of overweight trucks along different freight routes and highways. There's another view of the WIM dashboard to the right, a simple plot, graph showing the volume of trucks by class, 5 years apart, comparing those, and to the left, a sectional view showing different statistics by lane. An example of how we implemented one of our systems for a client at a signature bridge was due to contract conditions. They had this load rating permitting tool, so all overweight trucks that wanted to get a permit to cross the bridge had to apply for a permit, and then an already overworked DOT engineer or employee had to manually enter in the truck's information into a load rating tool that would spit out whether the truck was safe to cross the bridge, whether it wasn't, and then why, what part of the bridge was it causing problems for if it couldn't. And that current process takes about 30 minutes to process one truck permit. We wrote a Python program that ran through the entire vehicle history of the bridge, about 10,000 trucks a minute and 15 million in total, and ran them all into that load rating tool, and then summarized the data. Every truck that failed, plotted how it failed and why, and we were able to see we were able to provide estimates of if trucks had attributes within certain limits, that there was a high probability that they were safe to cross the bridge without having to manually enter in all the attributes of the truck into that load rating spreadsheet. Other trends we're seeing with overweight vehicles and trucks are an increase in truck weight in some locations, and along with that, an increase in tire pressure. And that may not sound significant, but as tire pressure increases, the area that load is spread from the tire onto the road surface shrinks, and that load becomes more concentrated. So that's causing some problems with some bridges, specifically some with steel orthotropic decks, where it's causing fatigue cracking due to that increased concentrated load. And that's a problem, and combined with truck volume, fatigue loads are highly dependent on cyclical loading. That just exacerbates those problems. Other trends we're seeing in the space are a slow but beginning to happen transition to EV semi-tractor trailers. EV semis weigh over 5,000 pounds more than traditional semis on average. And speaking of what we were talking about on the last slide, depending on where the battery is located on that truck, if it's concentrated in axle, that can cause even more problems. And to incentivize more EV semis and companies to invest in them, the government passed a law that allows them to weigh 2,000 pounds more at full freight than traditional combustion engine semis, which raised the legal limit to 82,000 from 80, which caused problems. Something that's not quite here yet, but could be here within the next decade, which is short in the lifespan of a bridge, is truck platooning, and that's where you have one driver-manned vehicle leading several driverless vehicles, and we're unsure of how that may affect our bridges as well. So in conclusion, WIM's about understanding both sides of the equation, the loads our bridges are going under and their strength. On top of the things we discussed today, it can be extremely useful in load rating applications where we have to determine postings necessary, understanding what loads are crossing over that bridge, what types of vehicles and how many can be extremely useful, or in site-specific assessments, whether that be for design of a new bridge, replacement of an existing bridge, or retrofit and inspection. Understanding the vehicles, like I said, and the loads in an area or on a specific bridge can help assign priority and direct money. And cloud computing really just amplifies all that. And that'll end it back there.
All right, so I do want to be sensitive to time because I want to leave time for questions at the end. So I'm going to cover extreme weather in about 10 minutes and the implications for cloud computing. So ultimately, extreme weather, all three of these are photos from Hurricane Ida when it went through New York in 2021. I don't know, some of you may have lived through that and had to deal with these issues. One of the Bronx parkways is flooded on the left, a bridge washout. I'm not sure where that occurred, somewhere in New York, I believe. And then the right is a railroad line for commuter rail where there was a washout. And this is one of the local news stories photos. And that's actually me with the backpack looking a little bit dazed and confused in this photo. If I'd known they were taking it, I would have tried to be a little more photogenic perhaps. But ultimately, this laid out three things for me. Number one, this idea of extreme weather really has direct implications. This is not design criteria percentage increase in our code. This is real extreme weather affecting real infrastructure. Number two, the hidden vulnerabilities within our system. This is one of many of the culverts on this rail line, and yet this was on no one's radar for risk. We simply don't know or don't have the technology at the moment to know where all these risks will occur. And then finally, the cascading impacts. But for this 10 or 20 foot span that failed, it stopped thousands of commuters from getting to work. And so we know that even small failures within our system, if our system is not resilient enough, can have major implications. And many of our linear assets, there's simply no better way to make them more resilient because of the current system that's set up. And so I'm not going to go in too much on the climate data side. Rest assured, it's going to rain more. It's going to rain more intensely. Much of the data points to that. This is something from two graphs of the EPA, with the blue line showing the past 30 years a significant amount of more rain. On the right, we see an increase in river flooding that was noted for over a 40-year period. And with blue arrows being the most intense, we see the Midwest, the Northeast, and the Northwest having demonstrated significantly more river flooding. This is some more data from Pew Research and from NOAA, just talking about the intensity of rainfall. I'm going to skip over this for now. Why is hydraulic resiliency of bridges and culverts so difficult? Oftentimes we think about the resiliency of these assets. Engineers think about them on the road corridor. Hydrologists think about them on the river corridor. We don't always have good correlation between those two. There are many complexities that change here. You could have a tree fall down in front of the river. That leads to greater change in hydrology, and it can be more difficult to assess the risk. And so there's many factors we can't understand, and it's also sometimes a very nonlinear response, where even a 10% increase in river water could have a major impact. And so we've really made it our mission to try to understand extreme rainfall better than we have before at HNTB. And one of the efforts is what I want to walk you through today. We all know, trust, and love the weather data on our phone. It helps us to live our lives and to know these things. That is backed up by various radar towers as well as rain gauges around the country. The good news is this weather data has been correlated by NOAA using one of their algorithms into a cohesive data set for the entire continental US. The bad news is it is only accessible, or at least numerically accessible, via these cloud search engine or cloud storage units. So every single hour of data is a single file, and it's in a format that's highly specialized, grib2.gz. So the problem would be, even if you want to understand holistically, not just a single storm, but what has been happening over time at various parts of a geography, you have to deal with every single one of these files. And so while this is highly simplistic, this is essentially what we were able to do using cloud resources and cloud computing. We took more or less a terabyte worth of these files, these grib2.gzs, looked at every single slice of time over a multi-year period, and queried them individually for all of the various bridges in a given state. This Massachusetts is currently shown. It's hard to see those little blue dots, but that's a national bridge inventory. So we queried 23,000 rainfall hours against 5,000 different bridges, and we're able to build essentially a time history, like a virtual rain gauge, at every single one of those bridges based on this data set. Now, it's not perfect, but as far as I know, this is the best data set that exists on precipitation. By doing this, we were able to then build a cohesive understanding of what events had occurred and have us better inform what are the risks of extreme rainfall on individual structures. This could be more broadly applied to other assets as well. And so why does this matter? The top left is a 24-hour rainfall accumulation from Indiana in 2022. That red dot there represents 10 inches worth of rain. That is 2 inches beyond the 1,000-year storm. What's telling for me, though, is not how much rain it fell, but how highly concentrated it was. Only a few miles to the east, there was no rainfall at all. This was a highly concentrated burst. It was not a named storm, it was not a hurricane. It was simply a flash flooding extreme rainfall event. It caused at least one fatality and washed out the bridge that's shown there on the right. A little closer to home, at the end of last September, we had a massive flash flooding event here in New York City. Grand Central was closed down temporarily. Many of our parkways were also closed down, and more than half of the subway lines were affected. So the implications for this rainfall data is not so much that we can forecast, not so much that we can look at near real-time data, although that is maybe possible as well, but it's that we can look holistically at what's been occurring and quantify these things based on that radar data. It allows us to test our various resiliency strategies against these and could actually guide future design criteria. And so this is a dashboard that we built to query millions of rainfall records, again, using Power BI and hosted by a relational database in the cloud, where you can actually look at all the rainfall data for an entire year, for an entire state, query it by the amount of rainfall and specific dates, and look at individual bridges and what were the peaks observed at that bridge. And so again, none of this would have been possible without cloud computing. Python was the back end for all of this work. We use cloud storage to be able to store these aspects. No machine learning yet on this data, but I think that's around the corner. And this is Power BI that we're showing. So really all these things coming together into this way to better understand this risk. And so on the extreme rainfall side, this is sort of my why does it matter slide specifically for extreme rainfall, but also freight data as well. When we put an Amazon warehouse in the middle of a cornfield, the local bridges on those routes may see a 1,000-fold increase in the number of heavy trucks. The bridge washout there is from Hurricane Harvey. This was a 250,000-year event by rainfall in some areas. These are both examples. Significant increase in trucks and significant increase in rainfall weather. Our code and our bridges are having trouble keeping pace with these changing demands. And so I believe the data we have is at least our best tool to understand and quantify these risks, and look at how the next 20 years will look nothing like the last 100. So I guess with that, we'll open up to any questions that the group has. Yeah.
So my question is more, I guess, about how do you get buy-in from a engineering consulting firm to do these types of projects? My experience with engineering consulting firms is that they think in a very specific way, they like their tools, they like their processes, and because few people actually have reliable coding skills, the ability to tap into these more advanced techniques, they shy away from them at the project level. How do you get buy-in from managers to invest time into this to build these types of cool projects?
Yep. So it's really a chicken and the egg problem. You can't do it if you don't have the skill sets. You can't get the skill sets if you don't do the problem. It really is manager, department, and even client specific. Some clients have very strict protocols on the way data is used, is QC'd, is stored, and is secured. Others don't have much of that. You know, we obviously subscribe to the best practices and protocols of the industry. Amazon and Microsoft are both very good about giving you the tools you need. The metaphor for Amazon is, we build a strong house, you have to remember to lock the door. So you have to have those things. It is, like I said, project specific. I think oftentimes we're trying to solve problems that can't be solved by conventional methods or not solved effectively. And so in those times, we've identified people, and really the sort of key for me, or one of the keys has been, I lead a small student group within H&TB. And so it's 15 or 20 engineers from around the country who all have an interest in this area. That's become sort of an informal network that we're able to use, but also gain skill sets and figure out who is doing this type of work, who needs help doing this type of work. And so really is about sort of a people network more than a computer network, and just having eyes for it. So approaching every data every project like a data project, and looking for those opportunities. But that is one of the key challenges here. Nail on the head. Yeah.
You mentioned the precipitation data from NOAA.
Mhm.
Is there any other like wind speed or thunderstorm data?
Yeah, so the good and bad thing about NOAA, the good thing is they have endless amounts of data. There's something called, I believe it's the NOAA one-stop API perhaps, or something about one-stop in NOAA, you'll find it on Google. And they've got every data source they have listed. I mean, thousands, if not tens of thousands. The problem is knowing which data sets are applicable to your problem. Certainly wind speed is there, humidity, surface temperature. They're leveraging both terrestrial situations like the satellites and rain gauges. They're using satellite data as well to integrate with that. Finding the correct data set and its limitations and knowing what that means for your analysis really is the tricky part. I have found NOAA, I would say, very amenable to conversation. So if you go, it's, NOD is the NOAA Open Data Dissemination Project. They're very responsive. There's the JPSS, which is a satellite group. If you're on a website, it has a comment section at the bottom or an email. More often than not, I reached out to the owners of this data set that I presented here. Within 30 minutes of reaching out, I had 3 distinct responses from different aspects of that team giving me feedback for free, and very responsive. So you can find what you're looking for, but it is a challenge sometimes to know which ones to use. Yep.
So you guys mentioned you use like motion data to evaluate these technical like over trucks, but like how do you guys like evaluate the condition of the bridges for deterioration of different parts?
Well, we have a whole inspection department, but we've done a separate presentation on structural health monitoring, which focuses more on the condition of the bridge and how it's behaving, and what changes we can see in the surface level acceleration or displacement data, but also the deeper data, whether the bridge's natural frequencies and stuff like that are changing. But to strictly rely on that, you're not at that point. But so usually when we check on things, it's usually manual inspections, and Eric has a lot of experience with that kind of stuff.
Yeah, so sort of the 3 buckets for looking at bridge deterioration would be number 1, visual, and that's the national standard. Number 2 would be non-destructive technology. And so this is things like ground penetrating radar, shear waves, and other methods to be able to use waves to see into there to look for voids, to look for areas of concern. And if you go to, I think it's the Federal Highways Info Technology page, I believe, if you just Google that, there's, 2 or 3 dozen various types of technologies and their trade-offs and limitations. That's one area for that. On the structural health monitoring side, SHM sensors can be used and often are used when there's areas of concern for the structure to both quantify and keep an eye on those. The challenge becomes we don't want to rely too heavily on those because it could be if the sensor we have does not predict the failure mode we're worried about in time, that's really not serving its purpose. So it really takes a high level of expertise and assurance to rely on structural health monitoring alone to look for deterioration. A good question though.
Can the existing weight motion technology be able to say this is electric truck or not, or you have to combine with maybe like license detection or other method?
Was it saying, can it detect if it's an electric vehicle?
Right.
Is that, not currently, because there's so many combinations of different axle weights. Is the truck empty? Is it half full? Is it overweight? If every truck, like the legal limit was 80,000 and stuck to that, and every full EV was spread at 82,000, then theoretically we could, but that's completely unrealistic. So right now we couldn't, maybe in the future, right now where the battery is located in the vehicle varies from company to company, but if it's all at the front axle, for example, and we're seeing high front axle loads higher than your traditional combustion engine, which is very likely, then we could say with some percent certainty this is likely maybe the cost.
Yeah, I would say also some states are experimenting with both computer vision and LiDAR to evaluate the truck, oftentimes for either being oversized or overweight as opposed to other aspects. But those could be if there's certain brands of trucks that have a certain, you could look at and know it's electric. We can then train a machine learning algorithm to know these types of trucks, especially with good training data, would be electric.
Because I do see some like logo detection of the truck.
Right.
That might be another way.
And I assume registration would differentiate that, but I'm not sure if that's the case or is the case yet. Were there any online questions that we have?
Not at the moment, so if you have one, make sure to add it soon and we can get to it.
Yeah, I might have a question, Eric. The topic that you discussed, I mean, the data, I think it, you know, when things like with the structural health monitoring and with the structural, I mean, with the way motion, it's expected, it is now that we have tons of data. So I mean, are there any like canned packages that can help the user, you know, don't have to worry about developing some of the routines, like the filtering, the programming that needed on those data servers, or everyone has to develop their own?
Yeah, so there's sort of two questions there, Dr. Nassif. I would say the first one is, can we pair weight and motion data with structural monitoring? We affectionately call it WIM-SHIM.
Right.
And I think that is something that can be done if you put the effort in to organize it. I have heard several manufacturers start talking about using actually computer vision to track a known truck across the bridge and its lane position, and then lining up that data with specific sensors. I have yet to see it. I've been told it exists. I have yet to see it work in practice and in reality outside the lab. And so I think that is coming eventually, and there are those thinking about that. I have not seen it personally. The other question is whether or not there's ways we can have this data without having to learn Python to post-process. There are a number of companies that are really taking structural monitoring dashboarding seriously. Eagle.io would be one example we've used. I know there's several others that are out there where you're basically buying it, software as a service, buying the dashboard to be able to utilize on your structural monitoring system. This can, I've seen, at least for some of these, show data in a more cohesive way, certainly better than just getting rows worth of endless data. But
Right.
oftentimes, if you want to do true analyses and zoom in on specific events, you do have to have the know-how to pull out the data and post-process it manually. At least now, in the future, I expect these will keep getting better.
That's great. It's good to know. Thank you.
Great. And we don't have any more online questions, so if there aren't any more in the room, we can conclude. So thank you everybody for joining, and to our presenters and co-hosts for today's webinar. Again, a recording will be available on the center's YouTube channel and on our website. And this webinar was brought to you by C2 Smarter, Rutgers, and the Rhine Bridge Resource Program. And stay tuned for news on future installments. Thank you, everybody. Have a good one.
Thank you. Thank you. Goodbye.